Introduction, Professor Choi. Hello, everyone, fellow students and professors. I'd like to express my big gratitude to Professor Choi and to give me this opportunity to have a presentation in front of you. So today I'm going to talk about the wireline transmitter to achieve 200 gigabps data rate implemented in CMOS, modern CMOS technologies. And mostly I'm going to talk about the challenges and overcoming design techniques to make it happen. So this is the outline of my presentation today. The main goal of this presentation is actually not to give you too much detail of the recent researches or industry activities, but to give you more like high level pictures of about what the service is actually look like and what are the trend is actually going toward. And then what are the insights and experience I gathered in the last decade working in Intel. So I'd like to use this as a good opportunity to share those insights from my experience and also discuss some of the design techniques I found. And then obviously I'll give you one example of the SerDes transmitter that we recently published in one of the conference. Then I'll summarize my presentation at the end. So before start my presentation, I'd like to use this as a good opportunity to advertise what I am in. So since I graduated a graduate school in 2011, I have been in organization called Advanced Design at Intel. So we are in Portland, Oregon, and then main goal of our organization is to first design the world-class I/O circuits, not even just for the serial interface, but also the parallel interface such as DDR or custom IOs. And also we drive the next generation industry standards such as IEEE, OIF, JDEC, and some of the Intel internal standards. And eventually we help define the next generation silicon technology from Intel by doing a lot of design and process optimization. These are some of the recent publications from our group. So if you are interested in our activities, maybe you can take a moment to look at those papers or presentations later on. So what is SerDes? The high-speed interface is actually everywhere in these years. And then whenever you want to transmit the data through the channel, you have to go through the serial or the parallel I/O or the interface, such as the CPU interface, PCI Express DDR, or high volume, high bandwidth memory interface are one of those. And if you look into the high bandwidth data center interconnect, there are like multiple protocols such as the Ethernet or OIF CI. And there is many emerging areas also. One of them is the automotive connectivity. In recent days, many vehicles have inbuilt sensors, cameras, displays that all need to connect to the electronic controls module through the high-speed interface, and also conventional CPU peripherals like USB, HDMI, or camera interface. And these all standard data rate or the global data traffic has been growing at a really fast pace in recent years, driven by high bandwidth demanding applications such as YouTube, Facebook, Netflix, Google. If you look at the data rate growth in recent years, it's amazingly fast. So we're talking about 100, exabytes in 2017. There has been more than 3x growth in 2022. And then all the standard data rate has been growing at the similar speed. And now we are talking about 100 gigabps per lane data rate in most of the electrical or even optical communication application. So the SerDes is actually meaning, technically it means any interface that serialize or deserialize data across the channel. So it provides a benefit to have fewer number of the pins to reach long distance for the communication compared to the parallel communication standards. And indeed, the serializing, deserializing speed determines the speed of the SerDes. So how fast you can multiplex data or demultiplex data determines the supported data rate or bandwidth of the entire SerDes. And because the data has to be transmitted or received through the channel, and this channel usually exhibits a very high insertion loss. And also the insertion loss is actually growing proportionally if you want to reach very long distance. So usually the SerDes phi, which is the combination of the TX or RX, has to provide some good equalization technique to compensate that channel non-ideality. And most of the times the feed for the equalizer is implemented in the TX side, and continuous time linear equalizer or decision feedback equalizer or combination of the FFE feed for the equalizers can be implemented in the RX side as well. So the goal here is to send the error-free data as fast as possible in long distance in a very power efficient manner. So when you design the SerDes phi, you have to be very careful to optimize all those parameters, um, obviously meeting the standard specifications as well. So if you look into the transmitter performance metric first, the jitter is maybe the most important metric you want to achieve, you want to meet, and then there is a certain maximum allowed jitter based upon all the protocols or standards. And obviously the bandwidth is another important metric, like it's shown as a swing or amplitude, and the peak value of the pulse response, and also the linearity of the transmitter determines the overall performance. And then the important measure of the linearity is probably the level mismatch ratio, or called RLM, or dynamic linearity called as SNDR, like a signal to noise and distortion ratio. And also the interface matching is important. And one of the metric to measure that is the effective return loss. So the channel and transmitter and receiver all both they should exhibit very ideal impedance at the interface so that you don't have too much reflection that eventually will degrade your signal integrity. And also the feed for the equalization capability in the RX. And also for the RX, bandwidth is important, and you want to achieve very good noise performance of the amplifiers. And that means also you want to have good linearity through that amplifier chains. And some of the equalization techniques are also employed, like the CTLE, and then you have to guarantee good peaking, like a location of the poles and zeros based upon the good signal integrity simulation. And then you have to achieve also good reflection in the interface. And for the platform designer, you have to be aware of the good loss profile of the channel, then the good discontinuity, like, the discontinuity has to be minimized whenever you design the channel. And also you care about the crosstalk when you design multiple channels, which is highly integrated. And then all of this together can be easily found in many modern silicon chips. For example, if you look at the desktop CPU in these days, there are many of the serial interface standards. For example, the PCI 3, PCI 4, or Thunderbolt, USB 2, USB 3, and DisplayPort, and HDMI, on-package I/O, or SATA. All these standards require a little bit different different bandwidth, but they all have the common thing that to increase the overall throughput at the interface. And then for the high performance server CPU, for example, the demand for the bandwidth is much higher. So usually they have multiple lanes of those high speed serial links to achieve very large bandwidth or throughput. For example, there are 64 of the lanes for the PCI 4, and each lane provides 16 gigabps per socket. And then there is FPGA chips and network SoC chips, and usually they require much higher bandwidth interface IPs. And then these days, Ethernet protocol standard of like 100 gigabps is the available standard in the market, which means that each lane has to have 100 gigabit bit per second data rate. And then when you have multiple lanes of that, you can actually increase the overall throughput. And the pluggable optical module is another important component of the fabric application, optical communication. And then if you look into the inside of the optical module, there is always the SerDes PHYs, usually including the clock data recovery circuits. And these days, this optical module can support up to 400 gigabit Ethernet maximum port speed, and each of the lane will support up to 100 gigabps data rate. So as I mentioned, the speed of the global, the data transmission or receive has been growing at enormous speed, and one of the indication of that is the maximum port speed growth of the network switch. So in 2009, we were talking about 10 gig Ethernet. Now in 2021, the global standard is around 400 gigabit Ethernet. There was 40 times increase within a decade, and that's actually amazing. That has been possible because of all the innovations and proactive research activities in academia and industries. And then we are facing very fast upcoming next generation standard, probably 800 gigabit Ethernet maximum port speed within a couple of years. And the question is how we can make it happen. So we can look at some of the publication trend also to get some insight out of that, the trend. So these are some of the selected publications in ISCC in past 6 or 7 years. And then you can notice that the IEEE 802.3 protocols trend has been going it has been grown by 2x at every 3 years. So in 2015, there were 25 gig Ethernet protocol, and after 3 years, the protocol achieved 50 gig data rate, or it required the 50 gig data rate per lane. And then 2021, the protocol says the per lane data rate has to be achieved at 100 gigabit per second. And then the state-of-the-art publication was always about 2x higher than that protocol. And first, about 50 gigabps SerDes circuits were published in 2015. And first 100 gigabps SerDes circuits, either transmitter or receiver, published in 2018. And 2021, there was a paper achieved 224 gigabps in modern CMOS technologies. During the same time, about 3 generations of the CMOS technology has been used for the fabrication of the chip. So for the most of the 25 gigabps circuits, 28, 32 nanometer CMOS technology has been used. Nowadays, most of the 100 plus gigabps circuits are utilizing 7 nanometer CMOS or even 5 nanometer CMOS technology. So the one is the fast data rate, and the other important parameter is how you can minimize the power consumption or the increase, maximize the energy efficiency. And that's even more important when you deliver the product onto the market, because overall the power consumption is directly related to the actual economy. You don't want to spend too much time on cooling solutions on the server if you have some IPs that burns a lot of power. So most of the IPs, the power consumption is kind of must have you want to achieve. Even though the data rate is high enough, you struggle a lot to design the circuit to meet that bandwidth requirement. But if your circuit burns ridiculously high power, nobody will buy that. So the trend to be very competitive on the market is that your transmitter receiver altogether has to show less than 4 picojoule per bit energy efficiency in a long reach application, meaning that the channel loss up to 35 dB insertion loss, your transmitter and receiver should send or receive error-free data. or for the short or the small insertion loss channel, 1.5 or even lower energy efficiency would be desired to be very competitive on the market. So the real competition is how you reduce the slope of this line, um, showing that your energy efficiency or energy per bit, like total power consumption normalized by the data rate, is actually proportional to the overall channel insertion loss. And then you want to find out good circuit design techniques or even architectural choices that brings down this slope a lot, so that you want to have a very power efficient solution. And if we talk about the Ethernet application, like the electrical link to support optical link, then there are multiple applications for that based upon the channel insertion loss. So the if your SerDesify support up to less than 10 dB channel insertion loss, for example, that channel application is called XSR. And then VSR, maybe you have to be able to compensate up to 15 dB channel insertion loss or profile. And for the MR, it's slightly higher. And for the long reach application, usually this channel includes the backplane copper channel plus at least two connectors and some the PCB loss due to the line card or switch card. So the total insertion loss is easily reaching about 35 dB at the Nyquist frequency. And for the data center fabric application, there are mainly two types of the solutions that are being proposed by industry. And one of them is the co-packaged solution. So in this case, you have ASIC chip and optical module uh, actually planted on the same package. And the interface between those ASIC and optical channel was implemented by another SerDes5 through the XSR channel. And the other solution would be called pluggable module solution. So you'd have ASIC, or you can directly drive the VSR channel to reach additional optical module in separate package. And that optical module would have additional SerDesify, or you can have some of the retiming SerDes5 in between to reduce or maybe optimize kind of the thermal uh, mechanics of your entire product. So for example, if you have the SerDesify built in the ASIC, for example, if they are monolithic implementation, if you have multiple, like more than 100 lanes of that in the same chip, you'd end up having large, heat problem, like, the thermal problem will be really headache for you to tackle. So sometimes you just want to put that in a separate chip and then put that through some additional channels. So for the 100 plus gig SerDes PHY, nowadays the DEC plus ADC based transceiver architecture is becoming an emerging architecture. So main reasons for that is the channel profile is kind of very nasty at this data rate. And then there's a lot of, some discontinuities and also the very high insertion loss through the channel. And then there is even very complex requirement for the equalization capability of your SerDesify, including the TXFFE and the RXDFE and FFE combinations. So usually to compensate those all the non-ideality of the channel, the number of the FFE taps required in transmitter side is actually increased compared to the previous generation of the channel. And nowadays for the 100 gigabps protocol, they require at least 5 FFE taps in transmitter. That means conventional analog-based approach might be less compelling to achieve good power efficiency. So to have more flexibility in the FFE implementation nowadays, many people they start thinking of having all the FFE functions implemented in the digital domain. So the DSP will take care of all the like FFE calculations and multiplication coefficient multiplications, and even some calibrations required for the good performance. And then the analog front end is just replaced as a DAC, so the digital to analog converter. So basically nowadays, the transmitter design is to design very high speed DAC to drive the channel directly. Similarly for the receiver, you'd have complex equalization function pushed to the digital domain so that you can combine a little bit of the FFE and also a little bit of the DFE based upon the overall channel performance you're targeting. And then the front end of the RX will be just ADC plus some of the front end amplifiers, which is working as a continuous time linear equalizer or variable gain amplifiers. And also you need a very clean or good, well-defined clocks to drive that. And PAM4 modulation was chosen for the 100 gig Ethernet protocol. And then now we are talking about the 2x higher data rate, which is 224 gigabps. And most like PAM4 modulation, that means the Nyquist rate of that circuit is 56 gigahertz. So the question is how you can design all these components in a very power efficient manner while meeting 56 gigahertz analog bandwidth. So in this presentation, we will focus on the transmitter side more deeply. That's where we found a lot of interesting insights, and then there are lots of things I'd like to share. But before that, let me briefly point out the design challenges using modern FinFET technology. So the FinFET is actually good, right? So many people know that the FinFET has a very good channel controllability, meaning that the transistor can turn on and turn off very quickly and then give you very good the leakage performance. And also the FinFET provides you very good mismatch property. So most of the circuits can operate at lower supply voltages while not worrying too much about the mismatch characteristic of your circuit. And the driving strength is increased from planar to FinFET so that you can build more powerful or the high intrinsic gain amplifiers. And then higher density usually means that low cost in terms of the fabrication. And more importantly, this technology keeps evolving in the same node to give you more like higher speed, better channel controllability, and driver strengths. But at the same time, there are some challenges to design very high-speed circuits using FinFET, and these are some of them, not all of them, but maybe there are many other things or aspects that I didn't include. But the first thing I want to point out is that there are many like bandwidth, noise, and linearity concerns when you design high-performance circuits out of the FinFET. And also, even though the low supply operation is desirable, many of the analog blocks or the mixed signal blocks requires to operate in a very high supply to guarantee good linearity. For example, the CTLA or DFE slicer output driver, you have to be careful not to compress the circuit too much by using low supply voltages. So most of the case that will bring you another problems, like you need to have multiple power domains for multiple circuits within the same IP. Then you have to be careful about reliability and also some kind of the performance degradation while you transition from one supply to the another supply. So everything will cost you complexity and power. So it's not always good. That's the point. And also the high drive current strengths provided by FinFET, and then very high density of the transistors. Sometimes it's acting like a big hurdle when you design very kind of the high performance analog circuits. For example, the IO buffer, the current does not scale too much, but your transistor dimension is scaled, meaning that the same amount of the current will always flow through the smaller area when you evolve from one technology to the another technology. Then you have to be very careful about like reliability of the transistor or interconnects, which includes the electromigration of the metals and the heat of the transistors, and also the aging degradation of the transistors, and so on and so forth. So you have to be aware of those reliability in the very early stage of the design so that you come up with a very good topology first, and also good layout, floor plan, and those kind of things. So I'll walk you through some kind of the design steps or the things to consider when you design very high speed transmitter, for example. So the goal is to achieve very good trade-off between performance, power, and cost. At the same time, we have to be aware of the reliability to make sure that the circuits will operate robustly through its lifetime, like 10 years or 15 years or something like that. For the transmitter first, you have to provide very good clock source. So the PLL or the phase locked loop will have to provide you very low phase noise clocks, and also it has to cover the range of the target frequency based upon the data rate. And the deterministic jitter should be very small out of the PLL, which is usually coming from the spur or the EM coupling of the inductors. And then you have to distribute the clock. Usually to maximize the data rate, a modern transmitter or receiver, they use the multiple phase clock. For example, the quarter rate transmitter use 4-phased clock. So that, which means that you need to provide some mechanism to generate those different clock phases. And also, when you generate those clock phases, you have to make sure that you are able to detect those clock phasing errors, and then you'll be able to correct it through some kind of the closed loop calibration. And jitter amplification is important because even though you have generated a very clean clock source in the beginning, if your distribution adds up too much jitter at the destination, then you will fail to meet the target. And supply induced DJ is important, but most importantly, you have to be very robust. And as I said, you need to have some sort of the detection scheme for that high quality clocks. And then your DSP will be implemented in a very low power consumption manner. And then it has to provide pattern generation, FFE, and memory interface and modulation. Sometimes you want to support multiple modulation schemes. And also you have many FSM calibration for the analog blocks. And sometimes people implement the pre-coding or channel shaping things by tweaking some DSPs here. And after that, you serialize the parallel data out of the digital block, and then those serializer has to be also very power efficient. And here you have to be very careful about the timing closure. And mostly the DEC will exhibit some non-linearity. So to compensate those non-linearity, sometimes different encoding is necessary within the serializer. So you have to be careful when you place those kind of the encoder not to break the timing and also minimize the power consumption. And eventually the DEC will have to have a good jitter amplification from the clock input to the output. And it has to achieve good like minimum swing specification and deterministic jitter, mostly coming from data dependent jitter or ISI. So you have to maximize the analog circuit bandwidth to minimize those effects. And these days, the transmitter RJ and DJ, those are equally very challenging to meet as the UI shrinks. Here in 224 gig transmitter, we are talking about 15 picosecond UI. So one unit interval of the data is only just 1 or 2 buffer delays we are talking about. So if you have a small bit of the delay, non-ideal delay component coming from your clock distribution, it's going to be a significant portion of your UI. So it's really challenging. meaning that we have to ensure that the analog bandwidth of the DAC and clock distribution, they all need to be, they have to be very sufficiently high. And also the linearity is one of the good big challenging to build a DAC. So we have to have good SNDR and RLM and the total harmonic distortions and so on and so forth. And then these are the performance metrics, but at the same time, we have to meet the functionality specification like equalization, step size, minimum, maximum step size, and DNL, INLs, and those kind of things. And the last but not least, these days, the data rate is really high, and there is a significant impact caused by the impedance mismatch at the output. And then the output pad matching network is becoming really important at this data rate. It has to provide good termination range and calibration. Also, the bandwidth has to be optimized for that. And ESD is one of the big challenge in I/O that you don't want to break down your silicon circuits while doing some fabrications. And DJ, such as ISI or group delay, can be degraded by wrong design of the output pad matching network. So eventually, your goal is to have good reflection performance by having additional matching network output here. So the first step, maybe as a TX designer, you have to consider what kind of modulation scheme you want to use. Sometimes you don't have to think too much about it because the standards already give you, hey, you have only one choice. You have to meet this, right? Your transmitter receiver has to be compliant with this modulation scheme. But as a researcher in academia, maybe you can think about very different, modulation schemes that can effectively increase the effective bandwidth of the circuit while maintaining good SNR at the output. I think that's a good topic in academia to figure out what's the circuit topologies or architecture with some kind of innovative modulation schemes. But here in industry, PAM4 has it has become as a prevail modulation schemes for up to 100 gigabps. And this graph, what I borrowed from ISSCC 2021 forum, is telling you very important characteristic of the modulation scheme versus SNR. So the PAM2, which is conventional NRG scheme, if you go from PAM2 to PAM4, actually, effectively, you increase the analog, you actually increase the data rate by 2x while maintaining the baud rate, the same baud rate, meaning that you just want to have the same clock distribution or analog amplifiers, which has the same bandwidth, but effectively at the output, you can increase the data rate by 2x, but the penalty is your SNR degrades. Now, because you divide the same voltage swing into 3 in PAM4 case, if you go up to PAM5 or PAM8 even, then you reduce the swing further, so your SNR penalty becomes higher. So the thing is, is there any way to increase the swing or increase the SNR when you're going to the higher order modulation? That is one direction. Or the other direction is, hey, I want to maintain the same swing, but I want to improve the other performances in the circuits to get overall SNR or the BER performance good enough for the communication. So when you talk about PAM4, there are some metrics that you want to achieve. So one of the linearity measure is called RLM, level mismatch ratio. So when you generate 4 different voltage levels at the output, either it's generated by analog circuits or DAC, it applies samely. So you want to have a very good separation of these channels. Otherwise, you'd have big eyes in the middle or small eyes in the middle, and your overall BER will be degraded because of that. And many non-ideal effects cause this issue, mainly the driver headroom or nonlinear terminations of the driver, or some bias current mismatch altogether. And the RLM was kind of the measure of static linearity. And then the another challenge for the high-speed DAC is to have very good dynamic linearity. And so here you see very good PAM4I diagrams. And then you do some linear fitting of that curve and extract one bit, like a single bit per response here. And then you can do like based out of that fitted curve, you can generate the difference between the original waveform and fitted waveforms. And then if you calculate the difference between those two, you actually get the errors in every data points here. And then you want to have small error. Like this is if you measure the standard deviation of this error, that's actually sigma E here component. So maximize SNDR, meaning that you want to maximize this first peak height and minimize this error. And why you have high errors here? Or actually there are two things. If you go higher and higher data rate, it's really hard to increase this first peak, right? Because this is the one of very clear, like, indication of your circuit bandwidth. So if you have a large RC effect at the output or at any kind of the internal nets, you'd end up having very small first peak. So these components gets reduced. And then whenever you have some deterministic zero in the interstage, output stage, they will show as an error, right? And then if you don't have enough time to settle to the required voltage level, meaning that your UI unit interval becomes very narrow, which is the case in the 224 gigabps. We are talking about only 15 picosecond. And any kind of that non-settled voltage will translate into kind of the jitter in time domain. So you will end up having large jitter, or not jitter, sorry, large errors, which is actually fundamentally caused by data-dependent zero in the intermediate stage or even at the output stages. So the question is how you can maximize the bandwidth of the circuit, which samely like how you minimize the errors and maximize the SNDR. They are all related. For the FFE, this is the concept of the FFE. For those of you who are not very familiar, so you just delay the input data by one UI, and having many of the delay taps, you multiply some of the coefficient there and then sum them at the output and send it to the transmitter. So when the receiver receives the data, actually the actual one UI pulse is kind of degraded to be like a skirt here because of the ISI effect through the channel. And this overlapped ISI will give you some challenge when you try to sense the data of this. So the purpose of the FFE is find out the good coefficient to cancel out this ISI in the first place. And maybe if you can't cancel the all ISI, the residual should be taken care of the DFE, the receiver side. But here in modern transmitter, the number of FFE taps are growing. So we are talking about at least 5 taps. So how you implement those 5 taps FFE in the transmitter, it's a good question, especially whenever you design very power efficient transmitters. So conventionally, those delay functions and multiplication of the coefficients and summations are all implemented in analog domain because it's efficient. You can have you can think of that all the multiplication in the digital domain is also very power hungry, but in analog domain you can customize it, and also the like a GM stage, some amplifier, you can actually implement those functions in a very power efficient manner. But when you increase those number of taps, actually some other issues just come up. One of them is these equalization taps are not always 100% utilized. Even though you want to generate good enough range for those equalization taps, some of the channel would not require all the equalization taps to function in 100% capability, meaning that you will be wasting some of the strengths of that because of some of those misutilization, and that's adding self-loading at the output and also loading to the clock distribution, and they are all power, right? So whenever you found wasted components, you have to eliminate that. So people started to think like, hey, I don't want to have that wasting loading at the output because of unused FFE taps. I just want to push that to the digital domain and design the output front end as just a DAC. And if you do that, you guarantee that the DAC always fully utilized, right? It's always gonna swing from 0 to whatever the maximum level, full swing. And the clock loading is maintained to be same, and you just save that based upon the maximum strengths. And now you care about some low power implementation of the digital, but in modern technology, you can actually have very low supplies, and all the standard cells, highly dense standard cells can be easily found to figure out good, like power efficient implementation for those DSP. So now it has become a trend for the output transmitter design. No matter what you have the topology for the transmitter, like analog FFE based transmitter or the DAC based transmitter, you would have to figure out what kind of the multiplexing scheme you want to do. So if you have a good clock distribution schemes up to very high speed, maybe 2-to-1 muxing scheme might be good, because it always gives you the smallest output loading, and then clock calibration scheme is very simple. Now you just have to calibrate the duty cycle of that. Now, oh, my clock distribution would be consuming too much power. I want to reduce the speed of that by half. Then I would not have too much zero amplification at all. Then good, right? Then you have to increase the order of the multiplexing by 2x. Now you have 4 input data coming, and use like a 2x slow data, slow clock to multiplex that. Then you have to provide good phase relation out of those 4 clocks. So the complex calibration scheme might be one penalty. And usually if you increase the order of the multiplex, actually, naturally you will have higher loading at the output because all these parallel circuits combined in together. So your RC bandwidth might be a little bit worse than that. And maybe you can increase one more order, have 8 parallel data coming in, and then use another like octal clock to serialize that. So you have to figure out what would be the good architecture that gives you best power and performance compromise. And then for the 100 and 200 gig application we found, this architecture is kind of good choice for that. And then after that, you have to figure out where you want to do that multiplexing. So one option is to do multiplexing at the very end of the circuit. So I call that at pad, or you can do that multiplexing in the intermediate stage and amplify that or buffer that and combine them at the output. So it looks similar, but there is a huge difference between those two solutions. Usually this architecture is proven very power efficient up to, let's say, 100 gigabps. And then we published this architecture in 2018 ISCC, showing the first 112 gigabps transmitter. But actually, this is the circuit implementation of that architecture. So the pulse generator is used to generate one UI pulse at the output. And then it's basically using the 2 edges of the 90-degree separated clocks. And then finally, one UI low pulse here in the node Y. Actually, the node Y is here, is generating the current pulse to the output. Which is going to the termination register. So you can think of that there are 4 of them connected in parallel, and one by one, it's generating one UI current pulse, right? So sequentially, it's doing the data serialization at the output. And this is very power efficient if you optimize all these circuits like devices to give you optimal loading to the clock distribution. And you only have one switching device in the critical data path rather than having multiple stacks. So your ISI performance is improved, and then overall bandwidth is improved. But going to the next stage, like a 200 gigabps transmitter, we thought it might be good to rethink or revisit this architecture again. One motivation is that this architecture, one of the disadvantages is that 3 out of the 4 quad slices are not active at any given one UI time. meaning that it's doing the equalization, the multiplexing at the very last stage at the pad, which is good in terms of the internal clock loading and pre-driving power. You have only one stage at the output, but you have extra loading at the output. Then if you found a good way to compensate that extra self-loading by having some inductors or some sort of matching network, it's okay, you're good. But at 224 gig, we found it's still very difficult. Even though you have some inductive peaking, actually 4x larger self-loading capacitance is going to be problematic. You want to reduce that, meaning that you want to have the dedicated output buffer and push that multiplexing into the previous stage. So somehow if you can reduce this passive components or size, or if you find out another active device-based technique to improve the bandwidth, it helps. It's actually better for the 200 gigabps transmitter. And next is the clocking. So the 224 gigabps transmitter, the clock, actually the jitter specification, jitter spec is really tight. So the total jitter is about 1 picosecond that we want to achieve. And out of that, RMS jitter around 200 femto and EOJ or quadrature jitter around 160 femto. Then you want to generate very low phase noise source clock for sure, but you also want to guarantee that jitter amplification through the clock distribution is very, very low enough. And the jitter amplification happens whenever you have the bandwidth limited circuits in your path. So if, when you excite very ideal clock, right, any kind of the bandwidth limitation will restrict this voltage will be fully charged to the supply level here. And any kind of the residual noise here will translate into the noise in the time domain. That will be shown as a jitter. So whenever you have the bandwidth limit, the input jitter is amplified to the output. Plus you have self-generated noise. So you can model this effect by having the jitter transfer function by inserting some input jitter impulse and then extract jitter impulse response at the output, and then do some mathematic post-processing, the MATLAB or some other tool to extract frequency response of the jitter. So usually you will have unity gain at low frequency, meaning that you don't have any jitter amplification, but that will usually increase whenever you go at higher data rate or higher frequency, and eventually it will go down because none of the clock will be propagated, right, in infinitely high frequency. And now you cascade those to model your clock distributions and figure out what is the good, like fan outs, like buffering, or what kind of the number of stage I want to have, I can have. And this is showing that even in the same similar tree, the clock distribution, if you have non-ideal fan out or very aggressive fan out, and if you have RC bandwidth in intermediate stages, you will have very high jitters at high frequency, which is called jitter peaking. So some people mitigate that by having different clock distribution architecture. And this is one example presented in ISCC 2020 by Rambus. So one can think of distributing source clock to the far lane at the speed, for example, 28 gigahertz here. But you can also think of generating low frequency clock by having another source PLL and then multiply that in each lane to generate the required clock. And by doing that, you can actually do some lane bifurcation here. So rather than generating the same data rate in each lane, you can actually change the data rate little by little in different lanes. Some usage case for the product that requires that kind of feature. And also your clock distribution would have very low jitter amplification here globally, but you have to budget the additional jitter added by ring PLL or local oscillator here, right? But if you can meet the total jitter spec out of it, this is one of the good candidates for the architecture. And what if you can actually attenuate the jitter? So rather than amplify the input jitter, you can actually attenuate the jitter by having inductive load at the output. And this is showing the CMOS, conventional CMOS buffer and the same buffers with the inductive load at the output. By doing that, actually, the jitter amplification is reduced. Not even reduced, it's actually become less than 1, meaning that your input jitter is attenuated through the buffer. That's because of the bandpass characteristic of the LC load at the output. So you will actually cancel the high frequency jitter when you have the bandpass filter at the output. And also the power consumption is reduced. That's because some of the inductive peaking will shape the output waveform to generate more like a class F amplifier. So the voltage waveform and current waveform in the inverter switch will lead you more like less power dissipation through the switch. So the overall power consumption will be smaller. And there is another jitter component, the quadrat jitter or even the jitter in the half rate transmitter. So when you send repeated patterns, actually, the different clock phases are used to generate those pattern or edge. And then if you have some misalignment between those 4 different clock edges, you will end up having large deterministic jitter at the output. For example, in the presence of the DCE or quadrat error, you will have unequally separated eye width. In order to cancel that, you have to provide good detection first, and then calibration scheme. So the output of the clock distribution might be good detection point, but there will be additional systematic jitter through the DEC or output pad. So it might be better to detect the jitter at the very output of the pad. Then you will have to provide some sort of the pattern filtering and some post-processing to distinguish where those jitter coming from. Is it coming from the duty cycle or quadrature errors? So those kind of things are good topic also in the high-speed SerDes area. And so this is one example of the clock spacing error detection. So when you have the asynchronous oscillator and make it sample the input clocks, you can switch what phase of the clock will be sampled, and then you can count the number of that sampled edges over a long period of the time and save it in the FSM and calculate what's the ratio between those two. And you can easily figure out, not easily, but relatively straightforward way that you can figure out duty cycle distortion. And for the quadrature distortion, you can do similar way, and then you actually count the sampled edges in overlap time of these 2 nearby clocks, so that you can figure out is there any distortion compared to the ideal 90-degree separation of the clocks. And the output driver is also very critical when you design the output, the transmitter. And the voltage mode driver is kind of the popular topology when you design very power efficient and simple transmitter. But it's a simple, but it's not always the best, because whenever you want to guarantee good linearity, you have to design these devices in a very large device to guarantee that any kind of the capacitive effect in the critical node will be mitigated out at the output. And also the linearity is a strong function of the ratio between this linear register and the device register. If you have a very small device here, any kind of the bandwidth limitation in the previous stage will show up as a severe linearity degradation at the output. Meaning that you will have a large device here, meaning that your pre-driver power consumption might be increasing because of that, and also the clocking load. So it's not always good. And the other constraint is that the output swing is closely tied to the supply rail here in voltage mode driver. So it's really hard to decouple this supply voltage from the previous logics. Usually these previous logics can operate in a low supply rail to save the power, and you have to provide a good, robust way to level shift between that. The other way is the current mode driver, the conventional differential pair with a bias current and termination resistor. And this is good because now you can just have a very low swing at the input of the device, and that usually provides you good bandwidth of the circuit. And the Another shunt picking inductor can be used at the output to extend the bandwidth, which cannot be easily employed in the voltage mode driver. So that's another good advantage of this. And usually the supply noise coupling to the output is smaller compared to the voltage mode driver. But here the linearity performance is critical because now you have to provide good headroom for the output. Now, sometimes it's done by having higher supply or even additional current source to boost up the common mode. And the intrinsic power consumption might be higher because of that. But you have to consider the full pre-driver and clocking load, and maybe the overall power consumption would be okay. And there might be another topologies, for example, the hybrid amplifier, which is taking advantage of those two topologies, but has a more headroom issue. And tailless NMOS switch, which have a very good, like, it can be implemented in a very power efficient manner. Now, where the pre-driver loads can operate at very low supply rate. And then you lose the differentiality of the circuit. So you may have a little bit higher common mode noise at the output. And then you have to control the output swing by having another cascode device on the top, maybe. And the output pad is also now the last critical thing going through the entire transmitter design. Now we are talking about 40 dB insertion loss of the channel from bump to bump. And then whenever you have additional, like, capacitance or non-ideality at the interface between the silicon and the channel, you will have a problem. So let's say you have a 40 dB insertion loss channel from the standard. If you add additional 200 femto capacitance at the pad, and then you will start breaking the reflection performance and insertion loss performance and so on and so forth. So you need to have a good the compensation techniques. And this is the example of 100 gigabps transmitter using, like, coupled coils, 3-segment coils to design the effectively canceling capacitance at every node, including the ESD diodes, C4 capacitance, and drivers intrinsic parasitic capacitance. And eventually it will increase the reflection from red to the blue. And also it will increase the bandwidth of the circuit, providing a little bit of the peaking here. And then also eventually the pulse height and quality of that will be increased because of the help of the output pad network. And then going to the next stage, like 200 gigabps, now we have to increase the order of the LC filter, and then the design methodology is slightly different. Now you have multiple sources of the capacitance, and then you want to generate good impedance matching at each LC segment. So you can think of this, as a kind of the artificial transmission line. So each LC segment has the intrinsic bandwidth, and that bandwidth is inversely proportional to the product of the LC. That means if you have a very small L and small C, it's better in terms of the bandwidth. But at the same time, the ratio between an L and C has to be close enough to the characteristic impedance to guarantee good impedance matching. So eventually, you just break out the capacitance components and insert some inductor components in between, and make sure that your entire passive filter generates very linear phase characteristic, such as the Bessel filter. And then we call this 9th order LC filter, mimicking the Bessel characteristic to get optimal jitter performance at the output. So now finally, I'll give you a very brief introduction of the most recent publication we had in this year, ISCC. So I'm not going too much detail of it because there is a paper already available on the online, and then you can download it and then you can watch the presentation video also. So we exercised all the design techniques that we already discussed, and then eventually the goal here is to generate good PAM4I at the output through the test platform channel. So the most challenging part for this design was to exercise very good jitter through the clock distribution. So our target was around 100 femtosecond, And in the measurement, we achieved about 65 femtosecond RJ, and then also about 200 femtosecond DJ. And the main point here is that we have the high-speed output DEC, and then the timing closure are all implemented by careful calibration of the clock faces, and then very low jitter amplification of the clock distribution, which is utilizing the inductive peaking of the CMOS buffers. So the clock distribution has dual path, HF path and LF path to support many different data rates. And also the clock demux and the clock mux is incorporated in between to have maximum the bandwidth performance. So each of them has the shunt and series peaking inductors in between, and the clock, the phase generation, multiple phase generation is performed by additional inverter or the delay cell, and we can modulate the capacitive loading or the inductor Q to change the effective delay through the buffer. And then we calibrate that delay through the FSM algorithm to give you good four-phased clock. And then additional inductive peaking in between stages, and to finally drive the output back with the satisfying jitter performance. Entire data path, really important is the data like timing. So here the so for UI timing window is kind of most challenging thing to close. So we have to provide a phase interpolator and phase rotator and find out the proper timing, the proper clock edge to close that timing without any timing error. And that's done by FSM calibration also. And the final, so DEC is implemented in, so it's in a two-stage topology. So the output driver is conventional differential pair and MOS-based differential pair. And the pre-driver performs 4-to-1 multiplexing. And that's actually a combination of the GM stage driven by the pulse generator here. And the output of the 4-to-1 mux bandwidth is extended by having additional active peaking device. So the impedance at node Y is boosted so that your rising edge, falling edge of the swing at node Y is fastened, like, it's improved so that you can effectively or very fast speed, you can turn on or off the next stage differential pair. And then the swing itself is not important because it can just be over the overdrive voltage of the differential pair. But if you have a high rising edge and falling edge, actually you can mitigate the ISI amplification from the node Y to the output. And also all the clock shapes are now close to the sinusoidal because of the extensive usage of the inductors through the clock distribution, meaning that you have higher sensitivity of the output voltage or amplitude to the threshold voltage of these NMOS devices. So effectively, you wanna have these transistors switching on and off with a very small VT effectively. That can be done by elevating the supply voltage a little bit. Like, you can think of that as the VSS regulator or LDO, so low voltage drop generator, so that you have certain DC voltage here, but the high frequency impedance is small so that you don't have any non-ideal effect in the high frequency toggling. But effectively, you increase the height of the pulse at the node X, eventually increase the bandwidth of the 4-to-1 mux here. And when you use the pulse generator to generate the current pulse, you have to be careful by choosing the right edge of the clock. Actually, you can implement additional clock jitter attenuation. For example, in this topology, the falling edge of the late clock and the rising edge of the early clocks are used to generate 1 UI pulse at the output. Here, actually, it's a little bit different. It's taking both falling edges of those two clocks and then generate the 1 UI pulse at the output. But the uncorrelated jitter can be attenuated if you use the first topology, meaning that if you have any uncorrelated jitter coming in the CK1 and CK2, the output jitters are actually 3 dB lower than the second topology here. So you would expect additional jitter attenuation and better performance. So the output pad, we had 5 capacitive sources and 4 inductor segments here. And then, as I said, this is the 9th order Bessel-like filter. So we put more emphasis on getting very good the phase out of that. And then the bandwidth peaking is implemented by that as well. And then for the EM simulator used to model this, and also the interface non-ideality effect between the package and the silicon as well. And this is the simulation performance of the output pad. And the group delay variation from the DC to Nyquist is maintained to be less than 2 picosecond. And finally, we measure the chip, and then here this is showing the micrograph of the chip, and this is like 100 gigahertz bandwidth oscilloscope, and we have a DUT here, and this shiny little guy is the package DUT, and then we have our own package connector to bring out the high-speed signal directly to the oscilloscope. So the measured channel insertion loss of this platform is around 4 dB at 56 gigahertz. And these are published in ISCC. So the clock pattern jitter we achieved is 65 in nominal condition, or even at, actually, I think my camera just died. I don't know. Yeah.
Oh, 네.
Okay, I'm sorry about that. I think I have an external camera here, but the battery just died. But it's okay. I just have one more page. So the clock pattern jitter 65 femto, and these are the measured PAM4 eyes. And then this is the first demonstration of the CMOS transmitter that achieved more than higher than 200 gigabps data rate. And then these are the measured clock phases, or the quadrature errors or duty cycles. And these are the comparison table. So we just looked at the first 224 gigabps transmitter. Then power efficiency we achieved is around 1.88 picojoule per bit, including the PLL. And all the critical performance metrics were met by having those kind of design techniques we discussed. So yeah, I shared my insight and some important things to consider when you design the high-speed SerDes transmitters. And then we have looked at some challenges as well. And then we have looked at the design example of 224 gigabps transmitter that we published in ISCC. And I'd like to say that more active research in academia is strongly desired to expand the scope and also the capability of this ultra high-speed SerDes circuits. So thank you. And this is the reference list. If you're interested, please take a look at those. And then, yeah, thank you very much. I'm sorry about the time. I think it's a little bit longer than 60 minutes, but yeah, thank you.
네, 감사합니다. 질문 있으신가요? 네, 별다른 질문은 없는데 제가 한 가지만 질문 드리면
네.
지금 일단 팸4까지는 사람들이 계속 사용을 하고 이제 스탠다드에서 계속 적용을 하고 있는데 이거 데이터 레이트는
네.
계속 올라가게 될 거잖아요. 어쨌든 그러면은 그 다음으로
네.
팸8 뭐 이런 것들도 그 연구를 하고 계시는 건가요?
네, 그거는 이제 보통은 이런 플랫폼이나 이런 채널 전체 링크를 이제 보시는 분들은 인더스트리에서도 그렇고 모듈레이션 스킴을 따로 보시는 분들도 있고요. 이제 보통은 이런 컴포넌트들을 설계할 때 그중에 이제 서킷도 있지만 실리콘도 있지만 아까 보셨다시피 커넥터, 그다음에 우리가 제일 쉽게 접하는 이제 PCB 보드 이런 것들의 인서션 로스나 이런 것들이 얼만큼 우리가 데이터 레이스를 더 뻗쳐낼 수 있는가에 따라 가지고 요걸 디자인하는 분들도 여기까지는 우리가 펜4를 서포트할 수 있겠다. 여기서부터는 밴드위스가 좀 줄어들었으면 아니면 이제 모듈레이션 스킴을 오더를 높여 가지고 밴드위스의 버든을 좀 줄였으면 좋겠다. 이런 식의 이제 디스커션은 스탠다드에서 이제 많이 하죠. 그래 가지고 여러 컴퍼니들이 모여서 그런 컨소시엄이 이제 형성이 돼 있거든요. 그런 데서 이제 어떤 회사에서는 우리는 팸6를 드라이브 하도록 좀 추천한다. 아니면 어떤 회사에서는 이제 우리는 그거보다는 뭐 팸5로 계속 드라이브하고 밴드위스를 2배를 늘리는 게 좋겠다. 여러 디베이트가 있어요. 지금 현재로서는 정해진 건 없고 넥스트 제너레이션에서는 아직 디베이트 중에 있죠. 예.
네. 사실 네. 그 거기 이제 마지막에 말씀하셨을 때 그 아카데미아에서도 여기 이제 울트라
네.
하이스피드 바이오 관련돼서 연구를 하면 그러니까 하는 방향 하면
네.
이제 좋겠다는 거 말씀을 하시긴 하셨는데 사실
네.
학교에서는 이게 할 수 없는 약간 제약사항이 너무 많은 것 같아가지고 이게 테크놀로지도 그렇고
그러니까 이제 제가 생각했을 때는 카메라가 돌아갔네요.
어,
죄송합니다. 제가 생각했을 때 그쵸. 이제 학교에서는 접하기가 힘든 게 보통 이렇게 하이스피드 서킷을 구현하려면 이제 최신의 테크놀로지를 써야 되는 게 이제 좀 어떻게 보면 자명한 사실인데 학교에서는 펀드 사정도 있고 보통 많은 회사들에서 이제 먼저 많이 잘 하고 있으니까 컴피티션도 세고 그렇잖아요. 그렇지만 이게 재밌는 사실이 저도 이쪽 썰데스에서 일을 이제 많이 했지만 썰데스를 잘하는 학생들이 굉장히 많이 귀한 것 같아요. 이런 하이스피드 서킷을 잘 디자인하는 사람들을 의외로 인더스트리에서 찾기를 되게 어려워해요. 그 얘기는 기회가 되게 많다는 거고, 그러니까 되게 빠른 스피드의 서킷을 만드는 게 다는 아니거든요. 우리가 이제 되게 머추어한 테크놀로지를 써서 뭐 지금 제일 빠른 트랜스미터보다 속도는 4분의 1밖에 안 나오지만 파워를 노멀라이즈 했을 때 파워가 훨씬 더 적게 나오는 어떤 아키텍처를 구현할 수 있다. 뭐 어떤 토폴로지를 가지고 훨씬 더 파워 에피션트하고 로버스트하게 디자인할 수 있다. 근데 그런 아이디어 자체가 되게 중요한 것 같아요. 그래서 어떻게 보면은 좀 더 아키텍처의 이노베이션은 이제 회사나 이런 데서도 뭐 열심히 이제 하고 있기는 하지만 학교나 이런 아카데미아에서 더 많이 드라이브를 해주는 게 그러면서 이제 인더스트리하고도 같이 의견 공유도 많이 하고 코워크도 많이 하고 그런 면에서 이제 서로 같이 발전을 하지 않나 그런 것 같아요. 그래서 보면은 단순히 데이터 레이트 스피드만 빨리 하는 것도 중요하지만 같은 더 낮은 데이터 레이트에서 얼마나 더 파워를 줄일 수 있느냐도 굉장히 이제 중요한 리서치 토픽 중에 하나거든요. 또 하나는 뭐 아까 제가 발표 중에 말씀드린 것도 있겠지만 클락을 어떻게 잘 캘리브레이션을 하느냐 이런 거는 사실 데이터 레이트하고는 크게 상관이 없거든요. 그러니까 얼마나 더 로버스트하고 얼마나 더 그 여러 가지 이제 실리콘에서 오는 여러 가지 넌 아이디얼리티들이 많은데 그런 것들에 별 상관없이 굉장히 심플하면서도 단순하면서도 굉장히 릴라이어블하게 그런 클락의 에러 같은 것들을 잘 디텍션하고 캘리브레이션 할 수 있는 이런 거는 데이터 레이트하고는 전혀 상관없는 거죠. 그러니까 아카데미아에서 굉장히 많이 잘 할 수 있는 분야고. 네.
네. 답변 감사드립니다. 네, 그럼 별다른 질문 없으면 네, 오전 세션은 이걸로 끝내도록 하겠고요. 그리고 오후 세션은 1시에 시작하니까 네, 다시 많은 참여 부탁드리겠습니다. 그리고 네, 발표해 주신 김지환 박사님께도 다시 한번 감사드리고요.
네. 감사합니다.
아,